Okay, continuing with our previous classes, we have now a new topic which is actually included in your operators in quantum mechanics. Expectation values of an observable. Okay, now what is observable? As you already learned it, observable, which is term included in your classical mechanics, in quantum mechanics it is your operators. Okay, that means classical observable is nothing but the operators in your quantum mechanics. Okay, let's come to the word expectation value. Okay, expectation value, actually expectation value denotes the average. Okay, average value of a physical quantity. Okay, so how we represent it, how we can represent this expectation value of an observable. Suppose I have an observable A. Okay, A, this is my observable, then its expectation value in quantum mechanics is denoted as in this way. Okay, so within this symbol you have to write the required observable symbol. Okay, so mathematically how we can define the expectation value? When a system is in a state described by a wave function psi, then the expectation value of an observable A of the system is given by A within this symbol, integration of minus infinity to plus infinity psi star, that means complex conjugate of the state function. Okay, and the operator psi d tau. I have taken the volume integration. Okay, A is what? A is your operator. Okay, and psi star is a complex conjugate of the wave function psi. Now here we consider that the wave function psi is a normalized wave function. Now if psi is not a normalized wave function, so in that case we have to write the expectation value of A in this way. A, have to write the normalization of psi is star d tau. Next, integration minus infinity to plus infinity psi star A psi, so d tau. So when we take in this way, when your wave function phi is not a normalized wave function. Okay, so for that case we have to normalize the wave function. So we have to divide this term, okay, this term by the normalization factor. Okay, let's take an example. Suppose we have a particle which is bound to move along x-axis. It is within the limit 0 to L. Okay, so the corresponding normalized eigenfunction, or you can say state, is given as psi is equal √2 by L sine n pi x by L. So in that case, according to the rule, suppose we have to determine the expectation value of momentum. Okay, so in that case we have to write expectation value of momentum is px within this symbol, integration 0 to L psi star, and you know this is the operator form of your momentum, okay, of your linear momentum, psi dx. Okay, now our work made easy now. Okay, so I have written this equation in explicit form. Okay, so I have put the values of psi star and psi. Okay, now I'm going to operate this term by ddx. Okay, so after doing all these things, you will get this equation. You will write in this equation in this way: minus I is cross 2 by L. Multiplying these two terms, you will get 2 by L, and also n pi by L term. After, how it will come? It will come when you operate sine n pi x by L by ddx, or integration 0 to L. Sine is already there, so sine n pi x by L cos n pi x by L. Okay, now we have to solve this integral. Okay, now perhaps you know from your trigonometric knowledge that twice sine theta cos theta is equal sine twice theta. Okay, so this formula we can use here when you insert this 2 within this integral sign. Okay, so applying this formula, I can write the equation I s cross n pi x by L integration 0 to L sine twice n pi x by L dx. Okay, we can write this here also, px. Okay, now after integrating this term, you will get actually 0 result, because you can see here when you integrate any function of when you integrate the sine function, okay, when you integrate the sine function, you normally get 0 result. Okay, so your final expectation value of your momentum is what? 0.